Hello there, and thank you for joining us. During this presentation and demonstration video, we aim to outline the progress and developments we've made as part of the CFLUX collaboration. My name is James Watson, and I am a representative for the CFLUX projects employed by Advanced Horse Sensors Limited, which is one of the collaborating companies and organisations involved. CFLUX is an Innovate UK project involving the collaboration between manufacturers and end users of carbon fibre composites, as well as electromagnetic Nd equipment specialists. There are numerous strands associated with this project, including the development of different eddy current probes and techniques for the inspection of carbon fibre materials and the detection and evaluation of flaws, material quality, etc. This project is tailored to the development of such techniques to address the gap in capability, reliability and performance of existing techniques using carbon fibre manufacturing and quality assurance processes. I will now pass you over to John Hanson, who will outline the progress and developments made in Ether NDE's coil-based eddy current system, working in close partnership with TWI.
Hello, I'm John Hanson, Managing Director of Ether NDE, and I'm going to talk about the robotic eddy current inspection of composite parts, which is part of the CFLUX project. The hardware is manufactured by Ether NDE and TWI Wales, and the components are manufactured by M. Wright & Sons and FAR Composites. In order to evaluate the system, samples were initially made in 2D, which were manufactured by M. Wright & Sons. M. Wright & Sons created 4mm and 15mm thick reference sample panels from woven carbon fibre material. These were then machined using a flat nose cutter to simulate delamination in the parts. The 4mm and 15mm panels had 6mm and 3mm square pockets machined into them of different spacing, sizing and depth. These reference panels were used to enable us to evaluate the new eddy current technology in relation to resolution, size of flaw detectable and depth of flaw detectable. The development of the eddy current system was undertaken at Ether NDE. At Ether NDE we designed a whole series of probes at different frequencies and different sizes, and also an XY motorized scanner for scanning the part. Here we see some fabric, but we also mainly did the solid material. This scan shows results taken with through transmission on a 4.2mm thick sample with 6x6mm holes, 2mm deep, so 50%. We used through transmission system 9 MHz probes with 8mm diameter, and that's what the results show. The smallest gap we can see here is roughly 1mm around about this part here. We also made a notched sample with various sizes of defects in it, and this is the scan. You can also see the fabric. And more recently we looked at some centrally placed 1mm thick discs of different diameters, the smallest being 2mm by 1mm high, which is this one here. For the proof of concept of the project, we're working on building a curved demonstrator test piece. The curved demonstrator is modelled on a fan blade from a CFM56. We're placing in this many typical volumetric flaws, as typical in carbon fibre manufacturing, and the design of the tooling to make this part will allow us to make different thicknesses of material. Further FEA work has also been performed on this, as well as tensile testing. The systems integration work is being undertaken at TWI Wales, currently in lockdown, and there we are developing a cobot system for application of new eddy current and magnetic flux technologies in order to automate the scanning of 3D composites. On the screen we see actually the 3D model generated when the scan is taking place. I will emphasize that this was our very first scan we ever did. and there have been no further scans done because A, we're waiting for the parts to be arrived, and B, software is being debugged, and COVID-19. The newly developed eddy-current probes are mounted on this yoke system here. I can run the video, and this shows data being collected and painted on the screen in a 3D model, and the idea will be that eventually we will be able to link the data gathered back to the FEA work that we've done and linking it back to working out acceptability of flaws.
Thanks, John. So here's just taking you through the ECMD side of the CFLUX project involving their development of coil-based eddy current systems. I'll now take you through Advanced Hall Sensors Limited's progress, where we've been developing the use of our quantum Hall effect sensors for carbon fibre materials. The company is relatively new to the NDT&E community, although the quantum Hall effect sensors they have developed and sell have been used in electromagnetic NDT research and development for the best part of 10 years, with millions to date being sold commercially to some big-name UK and international manufacturers. You may recognise the name quantum Hall effect sensors from other RCND and BNDT related events involving the University of Manchester, which is the academic roots of this company. The sensors use modern semiconductor materials to produce Hall sensors which are 70 microns in size and capable of 20 nanotesla magnetic flux density detection, that's 0.04% of Earth's magnetic field. As such, they can be considered more sensitive than coils of comparable size, with no frequency dependence, making them suitable for multi-frequency applications from DC to GHz. Their output linearity to field and their extremely wide 160 dB dynamic range makes them versatile and rugged to lift-off variations, offset cancellation, as well as enabling high-quality, high-contrast imaging capabilities. Their main drawback is the need for external electronics required to bias the sensor and amplify the Hall voltage signal acquired, something which silicon Hall sensors achieve using integrated circuits. As you will see, this drawback is negligible compared to the performance they can achieve using their combined sensitivity, dynamic range, linearity and compact size, which make them useful for various electromagnetic NDT&E applications, including the evaluation of carbon fibre materials. Using these sensors, the localized measurement of magnetic flux density, significantly different in operation to coils and other magnetic flux sensors, achieve very different performance and capability, which we outline here. Taking inspiration from the operation of alternating current field measurement, we have developed an electromagnetic Nd technique involving the use of a pair of illuminating coils to produce a linear region of eddy current. This setup has been designed to be used near DC through to 4 MHz, the optimum frequencies used dependent on the materials being inspected and the other NDT requirements and considerations. Perturbations within this linear region of eddy current are detected via the simultaneous measurement of normal and tangential components of magnetic flux density using 2 orthogonally aligned sensors. These measurements are recorded and compiled into magnetic field images for further evaluation using the positioning information received from the scanner motors. The distribution of the eddy current is highly dependent on the electrical and magnetic properties of the material. Based on the operational range of DC to 4 MHz, this technique is designed to be used for the NDT&E of numerous materials including steels, both ferrous and austenitic, aluminium and titanium alloys, as well as carbon fibre, essentially anything electrically conductive. For carbon fibre, we have found that this technique is particularly sensitive to the 3D orientation of individual weaves, relative to the directionality of the linear eddy current region direction in the y-axis. The left image shows that fibres that are aligned in the same direction, i.e. 0 degrees, to the linear eddy current region are well detected, since the eddy currents produce a significant response and those fibres perpendicular to the eddy current region are not detected. Moreover, the twirl pattern of this sample can be seen in the left image, where the undulations in the weave can be observed, where fibres being woven over the tops of others appear red, with the strongest magnetic field response, and those underneath appear yellow with a weaker magnetic field response due to a slightly larger liftoff. The non-conductive resin matrix is also observed in the background green between the fibres. The use of grayscale and simple reflectance image processing also emphasises the presence of fibre misalignment in the left-hand image scan data. As you can see, this simple image processing technique dramatically increases the visibility of fibre misalignment, shown as these white hotspots. The right-hand image shows a magnetic image obtained from the same clean sample where no defects were induced. Instead, the sample was rotated by 45 degrees so that the fibres were not aligned in the vertical direction, preventing the linear eddy current region from forming properly. In this case, the contact points between warp and weft fibres were detected, which appear as the yellow, stronger magnetic field responses, where in a small, localized spot a linear region of eddy current is still able to be formed and hence detected. At other points on the sample, where there is no electrical contact between fibres, no linear eddy current region can be formed, and hence the detection of weaker, i.e. background, magnetic field in green. As you can see, the magnetic images show that this technique can be used for the evaluation of weave structure as well as general quality. We intend to develop our image processing capabilities to add further impact to industry through the use of automated analysis processes previously published by other RCND members, including the use of radon and other transforms. The real-time image of the scan is being shown. Firstly, a lift-off map of the sample is compiled using the proximity laser on the same probe. As shown in the image output, there is some slight curvature or tilt to the sample from bottom left to top right. This is used to autonomously control the lift-off of the probe to maintain a consistent 0.5 mm above the sample surface, to not only avoid probe sample damage, but also for better quality images. The image appears grainy due to an 8-bit compression inherent to LabVIEW, which was used to control the scanner and generate the images. However, as you saw previously, the raw data from the scans can be compiled separately to produce significantly better quality images. The scan being performed is of a 50 by 50 mm area at 0.5 by 0.5 mm resolution at a frequency of 900 kHz. Due to the limitations of the scanner mechanism, the scan takes 8 minutes 34 seconds to complete. However, you will see that with a better manipulation system, this coverage time can be reduced significantly. This is because we determine the amplitude of the magnetic flux density generated by the eddy currents formed on and in the carbon fibre sample. As such, we require a lot less averaging than other methods which require determination of phase shifts. As such, we can achieve coverage rates of between 7 and 150 minutes per square metre, depending on the spatial resolution required, depending on the type of floor, evaluation necessary, and NDT context. Such, we believe that there is a genuine benefit to using quantum or Hall effect sensors, in that their characteristics provide a localized, sensitive measurement of the eddy current distribution, enabling a fast, non-contact method for flaw detection and material evaluation of carbon fibre materials via magnetic field imaging. In summary of the work performed by Advanced Hall Sensors Limited in collaboration with other partners of CFLUX, we have developed a new technique for the NDT of carbon fibre materials, which is also suitable for other electrically conductive materials. This technique produces high quality, high contrast eddy current images. Hall Sensors Limited intend to now develop enhanced imaging and analysis capabilities to support the evaluation of carbon fibre materials, as well as deploy the use of our 5 micron size sensors to explore their effectiveness in resolving individual fibres alongside even smaller, more sensitive linear regions. Finally, we'd just like to thank FAR UK and M. Wright & Sons for their help in manufacturing the samples used in this work. In conclusion, as a collaboration we have presented the developments of our technology for the NDT of carbon fibre materials using eddy current based techniques. We are particularly interested in gauging industrial interest, end user feedback and direction, as well as investment into targeted future development. We presented aspects of this work as well as other strands of the CFLUX project at the EASN 2020 conference in September 2020, the proceedings of which are being published later this month. On behalf of all of us at the CFLUX collaboration, thank you for your time today.